My name is Dmitry. I'm working for Intel. I'm a deep learning software developer and working with customers helping to optimize their workloads and the inference running on Intel hardware. In this session, I'm going to tell you more about what is Intel OpenVino, how you can use it to achieve the best performance on Intel hardware, and we'll show some samples and some real use cases with our customers where we was able to achieve really good performance improvements. So let me start from quick introduction. So OpenVino is a set of tools used for computer vision applications. It has two parts. First one is Intel DLDT, what is used to work to create application based on deep learning solutions. The second one is Intel optimized OpenCV and OpenVX libraries, what could be used to create traditional computer vision applications, plus could be used to do some image preprocessing, post-processing, and so on. So typically, when you are starting to create some project based on a deep learning, you are training your network, and at this stage, you might not care about how many servers you need for that, how many power they are consuming. If you need more performance, you can add one more node and do this in a multi-node. Power is important, but not critical at this time as a performance as well. So when you are starting to deploy your solution, the more critical power is coming to a more critical question. So you need to consume as less as possible. Plus, you would like to achieve the best performance what you might have on a particular hardware. And additional complications could be included in supporting different type of layers and primitives on each type of hardware you are going to use for inference. To solve all of these questions and some more issues what you might have while deploying solutions, we created Intel Deep Learning Deployment Toolkit, which is a part of Intel OpenVino. It's designed to make heterogeneous capabilities of Intel hardware more accessible for developers. It has pre-optimized plugins what could be used to run inference on a CPU, Gen, FPGA, GNA, MAVIDIOS devices. It implements frequently used type of layers or primitive with best performance in mind. Before I will start to talk more about deployment toolkit and how it's organized and how to use it, let me show you some real case studies what we done with our customers who started to use DLDT for inference. First one is GE City Scanner project. We was with DLDT and some additional optimizations what we contributed back to the product. We was able to achieve 14 times better performance if compared to baseline, just by, as I said, moving from TensorFlow to DLDT. As well, that was close to 6 times more than customer expected from this topology running on Intel hardware. So the target was 100 images on 4 Broadwell cores. That was expectations from the GE. We was able to achieve using just single core 150 frames per second, while 4 cores provided us close to 600 frames per second. Another recent case study with Philips. So we provided 2 models and we converted it to DLDT and run inference with some additional improvements, again, which we contributed back to the DLDT. We was able to get 188 times faster performance for bone age prediction model with the classification model used to predict bone age by using the input image, and was able to get 38 better performance for a link segmentation model. This is a semantic segmentation ResNet-like topology by, as I said, moving from TensorFlow to DLDT. And this is some, let's say, stages what we go through to optimize this model. So for Bone Edge model, initial performance was close to 1.42 frames per second. After converting this model and just run inference on DLDT, we got 74 frames per second. And after implementing and introducing some multi-stream inference using 2 sockets, we was able to achieve 267 frames per second for this particular model. On another long segmentation model, we started from 1.9 using TensorFlow, and just with running on the DLDT, we got 40.2 frames per second. And after implementing additional optimizations like using Vinograd kernels instead of direct convolution, we was able to achieve 37 frames per second. So a typical workflow of using DLDT for inference is look like this. So you have a trained model, which you trained with one of the supported framework. I will show later which frameworks we are supporting. And next, we are using a tool called Model Optimizer to convert this model from the framework format to the intermediate representation, what we are using for inference engine. Next, using inference engine APIs, you are writing application, which using inference engine and one of the inference engine plugin to run inference. So inference engine high-level architecture looks like this. So on top you have your application, which is using inference engine APIs. Using these APIs, you can load one of the supported plugin, what we have right now. This is a CPU plugin based on MKLDNN, plugin for running inference on GEN, based on a CLDNN, for FPGA based on a DLA SDK, for GNA based on GNA SDK, and as well we have support for Mavideo's devices using Miradex SDK. So idea of this product from the beginning was to provide the easiest way to move from one type hardware to another. And we achieved this. So if you are, let's say, testing your inference on a CPU, you can easily switch to GEN or FPGA just by changing one enumeration type and a function call, that's it. You don't need to customize your code for the particular hardware. Everything, all hardware optimizations will be done by the hardware plugin itself. So inference engine tasks is to take an input model and create some in-memory representation for this model for a plugin. It's with plugin, it optimizing inference execution for target hardware. So for CPU, it will apply some fused kernels, what is available for CPU, for GEN, the same. It's providing just a small footprint. Let's say if you are going to run the inference on CPU, this overall size of required libraries will be in around 50 megabytes. And this on the disk and in the memory, it will be the same. It provided just a small footprint. And as I said, it lets to switch easily hardware type by using a single line of code. So inference engine provides C++ and the Python APIs. C++ version is have runtime dependencies to C++ version, what we use to compile it to an inference engine. For now, this is a GCC 4.8 and above. For Python, we have support for Python 2, 3, version of 2 and 3. We are testing this solution using Linux-based operation systems like Ubuntu 60 and above, CentOS. As well, we have support for Windows and testing with Microsoft Visual Studio 2015 and 17. So to start work with DLDT, first tool, what you need to use is a model optimizer. Workflow is looks like this. We have a trained model. Now we are using model optimizer to convert this model. Model optimizer is not just converting this model, as well it's trying to optimize topology, doing some hardware agnostic optimizations, what could be utilized by any type of hardware plugin. It converts model from supported framework formats. It taking a framework format and converting to intermediate representation. It, if needed, can integrate right into the model mean and normalization. As well, it's doing some optimizations like node merging, batch normalization, elimination, folding constant paths, and so on. Right now, for current version, we have support for Caffe, MXNet, TensorFlow. From these, we have support for Keras as well, if it's using TensorFlow backend. As well, in the latest release, we added ONNX support. So using ONNX, we have support for Caffe2, PyTorch, and any other framework what can export to ONNX format. And plus, for some speech workloads, we have support for Caldi framework as well. Model optimizer itself written in Python, so this is a cross-platform tool. It has only dependencies from pip packages, depend on which framework you are going to use to convert the model. So for MXNet, it will depend on the pip package for MXNet, TensorFlow, protobuf for Caffe, and so on. So you can check the list of full requirements in the requirements.txt file. And the simple usage is like this. So you are calling model optimizer script, providing the name of the framework which you're going to use, plus a path to the input model. In most of the cases, you will see converted model in result. In some cases, it may fail if it will find some unsupported layer type, but we have extensibility mechanism which could be used to extend the support for layer types without waiting while our developers will add it. So after model conversion, framework model will be represented as internal representation, which has two parts. First one is a XML file, which storing information about layers, layer parameters like kernel size for convolution, paddings, strides, and so on. And the second file is a binary file. It's just a plain binary file without any, let's say, additional internal structure. It's storing information like convolution parameters, weights, biases, scale shift parameters, and so on. So internally, XML file will look like this. We have a list of the layers. Each layer is represented by a tag of layer with information about precision and the type. And as I said, it will store as well additional information depending on layer type. As for convolution, these dilations, kernel, strides, paddings, and so on. Plus, it's providing information about input and output dimensions for each layer. Another important information what will be included into XML file is the information about connections or edges. In this section, we see a list of the edges from layer, which means from layer ID to layer ID, from which port ID to which port ID. And plus, it can include information for pre-processing. In this case, we see mean values, what will be subtracted from the all input channels before the inference. So while after converting framework model into internal representation, model optimizer will try to optimize this model. As I said, this will be hardware agnostic optimization. So any type of hardware plugin can use these optimizations to speed up inference. First optimization, which is, let's say, more common for model optimizer, it's a batch normalization conversion to scale shift. After that, when possible, it will try to fold scale shift with previous convolution layer. It will just transform scale factor into weights of convolutions, previous convolution, and bias shift to bias. So this is how we can reduce number of layers, what will be run in the runtime. Plus, it will drop unused layers like a dropout and the paths what is not used for inference. So it will drop anything what is not related to the forward path. Plus, right now it can do FP16 quantization. This quantization is used only by Gen or CLDNN plugin right now. So this is example of batch normalization elimination. So this is actually that model from GE City Scanner project. It had some blocks like this. It's actually common blocks. You may see something like that in the ResNet-like topologies. So we have convolution. After that, we have batch normalization, ReLU, and pooling. After offline conversion using model optimizer, we will see only 3 layers in resulted topology. It will be a convolution, which was folded with batch normalization, ReLU, and pooling. The mathematical output from the convolution will be the same as from convolution plus batch normalization. So we are not cheating here. So for inference, when this topology will be loaded by CPU plugin, it will choose optimal kernel for convolution and ReLU and replace these 2 operations with just a single one, convolution plus ReLU. Which will help to reduce number of layers to be executed during inference. Plus, this will save the memory, because in this case, you don't need to create intermediate buffer for ReLU. By using this optimization, so when the first time converted model from GE, it was 10 times faster than baseline TensorFlow version. After applying these optimizations, we got additional 4 or in result 14 times better performance on this topology. Another type of optimization is optimizations what could be applied to ResNet-like topologies. ResNet will have batch normalizations as well, so model optimizer will convert everything into convolutions. And during runtime, CPU plugin will choose, instead of doing convolution plus altwise plus ReLU, it will do a convolution, and next convolution kernel will be fused with altwise operator plus ReLU. So in result, instead of having 4 layers, we'll have just 2. So we measured performance of this approach with a baseline, let's say not fused at all topology. After fusing convolution plus ReLU plus batch normalization elimination, we got 14% better performance on ResNet 152 topology. And after fusing convolution plus sum plus ReLU, we got additional 11% of performance if compared to the baseline performance. So let me tell you a bit more about inference engine APIs. So we have a trained model converted with model optimizer. Now we are using APIs in application to run inference on Intel hardware. So workflow will look like this. We need to load model and weights, set batch size if needed, load inference, one of the inference engine plugins. This could be CPU, GPU, FPGA, GNA, or Mavideos. You can use as many plugins as you want inside your application. Let's say you may have a situation when you want run one topology on CPU and another on a GPU. So no limitations. You can create once load topology and next load as many plugins as you want. And as many types as you want, I mean, within the single application. After loading plugin, we are loading network to the plugin. Next task is allocate to input and output buffers for inference. Next, before calling the inference, we need to put something meaningful into the input buffer. This could be image, this could be audio data, whatever. So we are not have limitations of input data type for inference engine. This could be any. It actually doesn't care what to multiply. And next, you are calling inference function and doing something with your output results. So this diagram is demonstrating what you need only once do these steps, like a load network, load plugin, initialize buffer, and somewhere in the main loop of your application, you are filling input buffer with data, calling infer, doing something with your output. This will depend on the type of topology you are using for classification. You will sort and extract, let's say, top 5. For the semantic segmentation, it can output the bitmap. For object tracking, like SSD, will extract bounding boxes and so on. So all will depend on application. So, and here is some sample code to demonstrate all these steps. So we are loading plugin using this function. Here we are providing flags D. In our samples application, we're using this flag to provide to pass the hardware type. This could be CPU, GPU, FPGA, or as well you can use a heterogeneous plugin and let's say to use multiple devices to run your inference, like GPA, CPU. Next, we are loading network using the path to the model. We are reading XML file plus binary file to load topology information. Next step is to configure input and output buffers. So we are taking input information from the network. It will provide us an input name, input precision, and the dimensions for the input buffer. Using all of this information, we are allocating buffer for input, the same for output. Next, we need to load the model to the plugin. We are using instance of the plugin and calling function load network and providing the instance to the network. Releasing pointers to free up some memory what was allocated to store network information. Next step is to prepare input. This code is from one of our sample applications. This code just reorganizing RGB data into RGB planar format, what is expected by the inference engine for image classification or image segmentation topologies. And the next step is to call infer function. We have two ways to do inference. One is synchronous APIs. So you are creating inference request and calling infer from this request. In this case, call will be blocked until infer will be finished. The second way is to use asynchronous API. So you can start async, call start async function. It will start inference somewhere in an additional thread. Next, to wait the results from the inference function, you need to call wait. Between those two functions, you can do whatever you want. Let's say you can start to read the next image. You can start post-processing for the previous infer request and so on. Plus, you can have as many infer requests as you need from a single plugin. So you can load one plugin and create multiple infer requests and do asynchronous APIs from the multiple plugins. For Python, we as well have a Python version of APIs, and we have samples inside the DLDT package. So the steps to use Python APIs the same as C++, but function calls is, a little bit less functions than compared to C++ example. So the same, we are loading CPU, we are loading hardware plugin. In this case, we have CPU. Next, we are loading network from XML and the binary files, doing some pre-checks what the input size and the output size is equal to 1. This is from our classification sample. Next, we are taking pointers to an input blob, output blob, reading image, putting it into a buffer, loading network to the plugin, and finally calling infer function. The same as for C++, here we have support for synchronous and asynchronous APIs. So to support, we understand what we cannot support out of the box, all the type of operation and the layers what could be used to run the deep learning topologies. For this, we created extensibility, which providing APIs to extend the CPU and the GPU plugins support for type of the layers. Plus, we have extensibility for model optimizer. For inference engine, you can use, as I said, for CPU or GPU, custom extensions what could add required support for missing operations or layers, or even or you can use these APIs to override existing operations. Let's say you have your very custom version of real operation and you'd like to replace the existing implementation. So you can use extensibility API to do that. For model optimizer, it could be used to add more layers what is supported by model optimizer. It provides extensibility on all levels, like front end, when model parsing is happening middle end, and the back end. As well, as I said, you can override some existing already supported layers. Let's say in this case, we have we had a power type for the layer, and we can replace it with a custom power, provide some data, and write extension which will be run. Then graph execution will hit this custom power layer. In this case, our execute function will be called. We can do whatever we want, and next return results back to the execution. So development extensions are really easy. For that, you have to inherit and implement IMKLDNN extension interface. This extension will be like a plugin to the inference engine. So if you have multiple custom layers, you need only once to do implementation for MKLDNN extension. For each type of primitive you are going to support, for custom primitive, you need to implement and override IMKLDNN generic primitive interface. And after implementing all of these, all you need just to call plugin, add extension, and provide a path to your extensibility library. So this from one of our samples. So here we are in MKLDN extension, just checking layer type, and if it's, let's say, custom power, a custom convolution, custom softmax, and so on, we are returning back instances to these classes, what will be used to run these operations. And for each generic primitive, let's say most complicated part will be just to implement the execute function. In this function, you need to do what operation is supposed to do. In this case, we have power operation, plus it should provide information about its expected input and output formats. So that's it. For CPU, we have CPU extensions example in a sample. It provides examples of implementation of detection output, ROI pooling, and some of the other layers what we are not supporting right in the MKLDNN. So you can use one of these layers to implement your own primitive, which we're not supporting out of the box from the NKLDNN plugin. For GPU extension development as well, very simple. So for that, you don't need to write any extensibility libraries. All you need just to create one XML file with kernel description plus CL function implementation for custom kernel. So in the code, it will look like this. We as well providing sample extensions for CLDNN. So this taken from the sample. So here we have operation what will replace the standard ReLU operation. It provides information about file name, defines some additional parameters what we can pass to this operation, providing information about output input tensors and work sizes and so on. And the second part of GPU extension will be a CL kernel itself, where we are taking input, output, additional parameters and doing some useful work. For model optimizer, we have model optimizer provides 3 types of extensions on, let's say, all levels. Front extension will be used on level of framework parsing and interpreting when the model optimizer is taking framework model and converting it into internal representation. Middle end, this is a level optimization of optimization what is using internal representation to do some optimization passes. Plus level of the backend. On this level, you can do additional modifications and let's say parse something, fault something, optimize some operations, and so on. So the simple extension for model optimizer will look like this. We don't have, let's say, out-of-the-box exponent layer operation support, so we can implement this using front-end extension like shown here. So we have a pattern defined for this operation. This will be exp function with exp operation. Next, then model optimizer will find this pattern. Exactly, it will find the name of operation. It will use a replace subgraph function where we can get information about input, create our operation, and replace existing operation in the graph. In result, this operation will be written into resulted XML file. So another interesting feature what we have inside the DLDT is the performance counters. So using performance counters, you don't need to use some, let's say, low-level debugging to understand what's going on with your topology. So it will provide information about each layer executed in topology, layer name, layer type, layer execution kernel, and the time of each kernel. Using this function, using this feature, you can track your topology and see which layers is taking most of the time from your topology, which layers could be optimized. Let's say for CPU plugin, it will provide information about which type of kernel was used. It was if it was used, let's say, reference version, you can do something with your topology and make it use some optimized version. So here is an example output from the performance counters. So we have here first column, it's a layer name. Second one is a status. If it will provide information if a layer was executed or optimized during runtime optimization. Type of the layer, total time taken to run this workload, average time per batch, average time per image, and the kernel which was used to run this operation. As well, using this performance counter information, you can summarize the output and see what, let's say, in this case, convolution takes most of the time. This is good. And if we will see something different, like, I don't know, ReLU is taking more than convolutions, we definitely have some problems in topology. This could be like an indicator. Plus, you can do a chart of top performers and see which layers is doing more job in this topology, and use this information to tune your topology and optimize it. For quick start, you can use one of our samples applications. We're providing applications for classification, object detection, segmentation, speech sample, extensibility sample. Plus, we have a validation app what you can use to measure accuracy for your resulted model, which was converted to DLDT. We have some materials on the website, including getting started, some frequently asked questions, samples, and so on. So you can visit our land page. It's softwareintel.com computer vision SDK, and get more information about where to get Intel OpenVino and how to start to use OpenVino. And I forgot to say it's free, and you can use it as some of the parts are already open source, like model optimizer. Some of the parts of inference engine will be open sourced in the near future. So welcome and good luck. Any questions?
The inference engine is supposed to run on the target. Let's say I'm running my videos on some obscure system.
So yes, on the target you need to deploy the inference engine to run the inference.
It will run on Raspberry Pi or some other
No, right now we don't have support for strange devices. But yeah, currently we have support, as I said, for CPU, GN, my videos, FPGA, but nothing else. To run this inference on a target system, you need to deploy inference engine. Good thing is it could be used to develop anywhere, because we have CPU plugin, and to use the CPU plugin, all you need just Intel-based CPU or x86 CPU. It should run on an AMD device as well. So, and next, after development, you can deploy this on your target machine with my videos.
Just the technical, when you get the asynchronous, can you do callbacks, or do you have to cut and just have it tell you when it's finished? Or does that not really make sense?
No, right now we don't have the callback mechanism, but we are, let's say, open for new features.
It's not specific to vision.
No.
Because speech recognition.
Yeah, mostly. Yeah, mostly it's used for visual workloads like classification, detection, and so on. But it's not designed to do only vision. It, as I said, doesn't care about what is input data, is it audio, video.
What about the network? Because vision is mostly CNN. Speech recognition from the other network.
We have some limited support for LSTM topologies, but we are working on this. Yes?
I can imagine there might be some restrictions using the FPGA as an inference engine. Is that the case? I mean, for example, let's say, I don't know, FPGA devices have varying amounts of resources, battery size and so on. Can you elaborate on issues that might arise with an FPGA as an embedded target inference using this platform?
For tasks like this, we have a heterogeneous plugin. Using this plugin, you can say FPGA and next CPU. If some primitive, for some reason, I don't know, too big kernel, too big output, too big something, it is not be able to run on FPGA, it will create fallback to CPU. And you don't need to care about this. You are saying FPGA, comma, CPU. It will try to create on FPGA. If not possible, we'll do on CPU. As well, we have affinity mechanism, so you can go through topology and say, you FPGA, you CPU, and so on. So you can manage this affinity by yourself, which layer will be run on FPGA, which on CPU, and so on.
So the affinity is sort of layer by layer, and data transfer is managed then.
Yeah. Ideally, it's better to, if you are going to use FPGA, do everything on a FPGA.
In practice, that's the way,
Yeah.
So that's why I mentioned about the fit issue.
Mm-hmm. But in some situations, you can decide to split topology and do some on FPGA, some on CPU. So for that, you can use affinity.
Can you put up that slide and show what frameworks are supported?
Yeah. One moment. Oops. Oh. This one. So on the top, it's let's say officially supported. Unofficial support will came from ONNX. At least we have a success with converting a V2 and PyTorch model through the ONNX path. So they're providing APIs to export to ONNX, and we're providing support for ONNX as input. Okay, thank you.